This is Rebecca Raphael with my Physics Lab 11. I analyzed a video of a boy jumping off a 5-meter diving board, and my problem was using a real-life model of projectile motion in order to make predictions about the initial conditions, specifically the initial velocity. The relevant fundamental principles that I used the momentum principle, which is delta P equals F net delta T, and from that you can derive that the position at T equals the initial position plus the initial velocity times delta T plus 1/2 F net over m times delta T squared. The main result was that using the formula that was derived from the momentum principle and using conditions from the experimental data, I was successfully able to predict the initial velocity of the boy. Here is the video of the boy in Tracker. I used the calibration tool to calibrate that he was 5 meters from the ground because there's a 5-meter diving board, and I set the axis system. So I traced his center mass as he jumped, and Tracker put in the data for me. As you can see, it's a parabolic motion, and at time 0, x was 0 and the y was 5 because he was 5 meters off the ground. And then at the final time, 0.967, he was at a y of 0 and an x of negative 3.776. So I used data from Tracker and I plugged in all of the initial conditions, which I just talked about, and the F net was negative m times 9.81 because it was mg was the only force acting on it, and the actual mass of the boy doesn't matter because, as you will see when I show the calculations, it cancels out. And then we don't know the initial velocity, which is what I'm going to find in order to model it. So on this slide, I calculated the initial velocity using the equation that was derived from the momentum principle. So for the x component, you only use the x part, and so since he started at 0 and ended at negative 3.776, you just plug in those numbers, and the final time was 0.967, so that was the time that passed. So here we have that the velocity initial is going to be equal to negative 3.776 divided by delta t, which is 0.967, which gives a velocity initial of negative 3.9 meters per second. And then for the y component, you do the same thing, but for everything in the y, but there's actually a force acting in the y component, whereas in the x there was not. So here you have 5 as the initial, and you have the velocity initial you're trying to find times delta t minus 1/2 times 9.81 times t squared, because the F net is 9.81 times the mass, but then it ends up getting divided by the mass, so it cancels out, so the mass doesn't matter. And then once you plug in all of these numbers, you get negative 0.43 meters per second. So here is my code, and I plugged in all of those initial conditions, that the ball was 0, 5, 0 for the position, and the vector for the velocity was negative 3.9, negative 0.4270, which are the ones that I found. And when I run my code, you can see here's the projectile motion. This looks the same as the boy did when he was jumping off. And here is a graph of the time versus the y position. I had my code spit out the data, the model data, which is this data on the left, and then I also got the data from Tracker, and I graphed both of them. So here you can see that the model is the blue and the experiment is the red, and that they are very similar, and that they start at 5 meters above the ground and they both end at 0. So they're extremely similar, and the only difference would be because of the slight difference caused by the force of air resistance, which I didn't account for in my model. So here is a larger image of the graph where I compared the experiment and model data. And as you can see, this shows the main result, that you can use conditions from experimental data of projectile motion to predict the initial velocity of the boy. So that's pretty much my lab. Thanks for watching.